Okay, so last time we talked about a proof of the Van Kampen theorem. Proof of the VK theorem. Or at least a general version of it, which we can apply to any Femboy space that we want to sort of find the fundamental group of. So we're going to move on and go take a revisit to the foundations of our theory, and we're going to revisit some ways or some constructions we can do on our given subset of fundamental space of all femboys. Of course, equipped with its own special topology. So the main focus actually of this video is the quotient space. That's the main focus of today's video, quotient space and our application of it into our theory. So we essentially have an F space, and then we quotient it and see what happens after we apply the quotient on that space. And so this is a very important prerequisite to formally discussing about gluing things together. Now I have talked about gluing things together already before, especially during the Van Kampen theorem, right? Things like wedge sums and stuff like that. Wedge sums is that we just glue it along a single point, right? We identify 2 points, or at least 1 point, one distinct point from two spaces, and then we say they're just the same under some equivalence relation, right? And that essentially tells us that the two spaces are connected at that one singular point, or at that one new element which we constructed from identifying those two distinct points. So before we get to actually discussing the foundation for formalizing gluing in our theory, let's take first a review of what we know thus far on constructing stuff out of a space, or constructions we can do on a space. So the first possible thing we do, so let's first consider a space or a subspace Q of the fundamental space of all femboys F. Okay, so Q is this, alright, let Q be that, and then let's say for now it is just a set, right? It's an unordered set, and then I want to apply order on it. So it's very straightforward when you want to employ order on a set. What you just have to do is say that for any A and B inside Q, there exists an operator which I will call less than or equal to, or no, so there exists an element which takes AB and maps them onto A less than B, and it does another one, so it could possibly be that, or AB gets mapped onto B is less than A, and there exists, of course, the same operation but with an equal sign, such that AB is mapped onto the same thing, B is less than or equal to A, and of course there exists the exact same operation that takes AB and maps onto, this time, A is less than or equal to B. So I just have to say, this is the first criteria first, that there exists a relation like this, right? For any two AB inside the Q. The second condition I have to employ is that if for these two AB inside A, X is not equal to Y, so there exists another relation between A and B. I mean, this is one relation, it's an inequality relation. This time, we say that there exists, so okay, not just that, but there exists an equality such that it maps AB onto A equals B. Okay. And of course, there exists an inequality version of that wherein it's a negated form wherein A is not equal to B, right? Though, you could say that this is a subset of one of these two relations here. We just say that these two hold, that these two are true, or are true for this AB. And that would imply that if B is less than A and A is less than B, then it must be that they're both equal. So it sort of negates the inequality and just say B is equal to A, because they're essentially the same, they have essentially the same measure, right? So this is a special subset of this. If I combine these two together into one singular definition and say B is less than A and A is less than B, less than or equal to B, it just negates it and gives me this string. So I really don't need to write this, but I'm gonna write it just in case. Okay. So the second criterion is to say that if for these two A, B inside Q, of course, X is not, or A is not equal to B, then it must follow that, you know, A is either less than B or B is less than A. Okay? So if without this, or these combined without the equality operator, it would only have to be either of these two. Okay? So if I combine these two into one singular string, right? Or say that B is less than A and A is less than B, so I require that these two have that intrinsic property of being less than each other, then it must be that A is equal to B. But since we're saying in this criteria or this rule that A is not equal to B in that case, or in that one singular string when I combine these two maps together, then it must be that the equality is removed now, and it must be that there really is an inequality, that these two are not precisely the same, you know, or they don't have the same measure if we have a predefined measure on Q, of course. Now, if I say that Q is a subset of FRN, I mean, of course, there's a predefined measure. I can use the Lebesgue measure on this. So I can take the lambda, just lambda, because, you know, every subset of the real numbers satisfies the Carat-Theodori criterion, which I will discuss in another video about cuteness and stuff like that. So, yeah, I can take the Lebesgue measure of Q, and it will precisely be the length of Q and stuff like that. If it is part of FRN, of course. So, that space has been discussed in Femboy theory already. So, if you guys are quite rusty on how to use FRN or how to construct it and what exactly it is, you guys can give that a read. So, that's one example of an application of this order over here. If I have a measure, a predefined measure, in this case the Lebesgue measure, of course. If I have two subsets Q and, or if I have two elements inside Q, right, two subsets Q inside R, let's say an interval inside it, and then these relations should hold, right? So if I have two intervals that are exactly the same, it must be that they cannot be less than each other, right? That wouldn't make sense, right? It's like saying that something that's short is shorter than something short is shorter than something that's long, but that long thing is shorter than the other one. So which one is short and which one's long? So it doesn't make sense. That's why it breaks down. That's why it breaks down, and that's why we require this this second rule. Okay, so the third and last one is this transitivity. So I have three elements now, given an A, B, and C inside Q. If A is less than B and B is less than C, then A is less than C. If I'm correct. Yeah. So just like how, you know, A plus B, just like how if A equals B and B equals C, C is equal to A, or A is equal to C, doesn't matter. The same thing carries on with the inequality relation. Okay. So let's say that A is 1, 2 is B, and 3 is C over here. Then of course, A is less than B. 1 is less than 2. Right? Assuming that 1, 2, 3 are real numbers. Okay, they're real numbers or they're integers, and they're symbols for, you know, those concepts, and they have order on them. Okay, I'm just being specific because someone among you can tell me that, oh, it's just a symbol, it's not the actual number. I'm talking about the real number. Okay, so 1's less than 2 and 2 is less than 3. Then of course, obviously by common sense, 1 is less than 3. So the rule really holds, and it must hold actually in order for things to make sense in our space. So these are the three rules I want enforced in order to create order on my set. Okay, so the actual construction starts here when we define the basis of the topology, and then sort of make the topology from there. So I'm just going to define the topology now, or the basis rather. So the basis for my ordered topology, this is what we call the ordered topology, is this set. So the set xy, or a set of all ordered pairs xy, of course xy inside Q, such that x, it's either x is less than y, x is less than y, right? For x and y in Q, union the open set. So all these are open sets, by the way, because over their basis, they have their basis of topology, so they must be open sets, okay? And it makes sense, it's interval, or it could be thought of as interval, or actually it's a pair of numbers, of course. So two pairs of numbers from Q2, of course, or Q cross Q. And then so next, we want a base point. So I'm going to define a base point x naught, and then I have a y. So this time this is an interval points. This here could be actually this is an open interval points. Yes. Most open sets in topology are defined by open interval. So don't think of this as a pair, but as an open interval. Okay. So this time I have an x naught, a different element from x, and I have my same y over there, and it's a pair. It's a set of all of these intervals, of course, such that x naught is less than y if and only if, if and only if there exists an infimum of Q, which is defined to be x naught. Okay. So if I were to include x naught into this part of the basis, it must be that the least value of Q, or if we have a predefined, smallest value in Q, right, or subset of F, or fundamental space of all femboys, then it must be that this base femboy over here, or this base femboy x naught, is the least femboy, or the very first, you can say. But we don't really have a notion of first right now, okay? Because this is not linear order or lexicographical order. And we will talk about lexicographical order in just femboy theory as a footnote, okay? And then one more union, we take one more union to complete the basis. Union, and then this set. So it's the opposite now. So instead of having a base femboy here, we have to define a supremum, we can say a greatest element. So the last element, you could say, or the element that no other element can exceed, okay? So actually, in this case over here, for the real numbers, of course, extended real numbers, of course, or the affinely extended real numbers, which includes minus infinity and positive infinity, because the real numbers original doesn't include those two. Our infimum would be minus infinity, and our supremum would be positive infinity, okay? But really, there is no distinct basis for the ordered topology on R, okay? So, okay. So we're going to do the opposite now and say this time x is open and then y not. We have another sort of base femboy, or another femboy which we call to be the last one, or we call the supremum. And then we need the crucial relation, x is less than y not, if and only if there exists a supremum of Q, which is defined to be y naught. Sorry, excuse my nephews. He keeps blasting his loud TikToks, I swear. It's a bit annoying. Okay, so what we essentially did in constructing the basis for our ordered topology is that I have every possible open set in my set, such that the relation holds, or I have this relation of x being less than y. And then now I define a smallest element inside my ordered set, which is x naught, okay? And yeah, because originally our set is unordered. We don't know which element inside is the first and which one is the last, right? So we need this notion. And then the last thing that we needed to do was to define what is the last element, all right? So we needed to do. So this is what this is for, and that's what that one was for, I guess. So this is the every in between. This one is the first element. This was the last element, and that's what we need to do in the basis of topology. Okay. So the real order topology is constructed. This is a basis only, and the topology that is generated or that this generates is the order topology. So when I equip, so this generates my tau less than. I'll call that my order topology. So it generates that, and the construction, the first construction that I will discuss today, of course, is the order topological space. So Q equipped with that topology. So that's my first construction, which is of course, yeah, first thing to do. Now, this is not something that I'm assuming in the next few constructions, of course. In the next few constructions, I'm assuming a space that isn't really, that isn't ordered, okay? So this is just for this example. Alright, so let's get to another construction. And this construction is actually very, very important, very common in topology, alright? And this is the product topology, alright? So now, let's consider the simplest case. Okay, I have a line of points, a line of femboys. So I have Q, of course, inside F. But it's just F. It's just strictly a line of points. So with a of course, X naught, base femboy, and then a last femboy, Y naught. Okay, but this doesn't imply that this has the order topology. Okay, it doesn't imply that. All right, so what exactly happens when I take one point or one femboy here, right? And then I take another distinct femboy from that, and then I pair them together. I make a couple out of them, or an abelian block out of those two. And then I order the abelian block, all right? And it essentially becomes a coordinate, right? So what we mean by that is called a Cartesian product. So a Cartesian product between, you know, this set with itself is the set of all possible pairs of distinct points coming from it. So we now think of a square. So this is Q, this is Q again, and then this is Q cross Q. Now this is not like multiplication, like, you know, multiplying a number this amount of times. What we mean, of course, is take two distinct points or two distinct femboys and then put them into one singular pair. And this is what we get. I'm sure we could discuss this in femboy theory, so it should be a trivial topic to you guys. Okay. Femboy theory. Okay, so the thing is, when we do this, alright, we cannot just say that the topology, you know, the topology of this and the topology of this space and just product them together. We can't just do that. We can't just take the basis or the basis of those topologies and then stick them together into a Cartesian product. We can't just do that. We have to define an entirely new topology such that we have open sets that are two-dimensional, geometrically speaking. Or generates a volume element, topologically speaking. So there. So let's do that. So new basis, and this basis is gonna be, okay, I have two subsets, mu, or two collections of femboys, mu and nu, that's inside Q. Rams doesn't. Okay, so what I'm gonna do is take the Cartesian product between these guys. So it's all open sets, mu cross nu, such that of course mu inside Q, and so is nu, and of course those are both open in Q. So they're both open in Q. And that basis generates the product topology of the two. that's another construction. Oh, of course, there's another way of thinking this, of course. This is just a square, right? This is a square. If it's running from 0 to 1, or if I create a bijection between this interval and the interval 0 and 1, then I suppose this would be the unit interval. So it's the unit square. Yeah. So last thing I do for this second construction is, of course, the topology generated by that. And then I just equip it with Q. Of course, Q this time is not ordered. I'm not requiring the Q is ordered this time, though you can say this. Tx. That is the product topology. So it's a second construction. Another example of this is that I have a long interval, and then I have a short interval, and then I take their Cartesian product. So what we get from there? Of course, we get a rectangle, but we have to use or employ the product topology. So whenever we do something new to a space, aside add elements into it, of course. Oh, of course, all we have to do is say the element is inside one of the open sets of the topology. It's as simple as that, right? Aside from that, those trivial constructions, right, or taking away an element from our underlying set of the space, these things require new topologies in order to function. And yeah, that's one of the most important things that I learned from topology, is that when you construct stuff or do non-trivial constructions on space, like say products, or maybe even quotients, as we will discuss later, or taking away subset, which is the next example, you will need a new special topology on that. So now, I just mentioned at the beginning of this lecture that Q is a subset of F, or a subspace, we can say, because F can be interpreted as a topological space, right? It could be interpreted like R, and then Q is a subset of that R. I just showed you guys a while ago, and in the previous theory, or in the previous course, that there is a bijection between this and the real numbers. And in fact, the set of all symbols inside this that has a bijection or has a pair in R, or has a respective version of themselves in R, compose a new set, FRN. So, alright. So now what we're saying, it's a subspace, right? It's a subspace. So we take away a space from it. So what do? We just take away a piece of the topology? We can't just do that. That's going to break one of the rules of a topology, which means that the entire set is inside it. So again, we have to do stuff again. So we have to construct it from the ground up. We have to define the topology, because we cannot just modify the topology of F itself in order to get the topology of Q. We have to do something new here. And that's the idea of the subspace topology. Okay? So F is our topological space, and of course Q is our subset of F. I'm gonna now define a new topology. Okay? So I'm not gonna start from the basis this time for the lack of time, but I will start with the topology. And in fact, it's best to just start with the topology. So the topology of Q is defined to be Q intersect mu, such that mu is inside the topology, tau, topology of F. Okay, so this is the topology of the subspace. So I have elements in Q here, and I have elements of an open set inside the topology of here. I just take the intersection, what's common among both them, and then make those my open sets in this topology. And it's as simple as that. Just equip Q with this so-called subspace topology, and then we get a subspace, a topological subspace. And that's the third construction. Very simple. But the basic idea behind it is a bit elaborate, and that we needed to do something new and stuff, just take away something from the topological space. And I urge you guys to check that, of course, this definition of a topology still satisfies our axioms of topology, or of what topology is. Now there are many other topologies. Of course, the metric topology. All right, there's the metric topology. There's the lower limit topology, What else? Yeah, the metric topology is very important when we discuss about, or when you want to discuss about openness. Not only openness, but balls and continuity. What else? Yeah, there's the metric topology. A uniform topology, of course, the standard topology in R, Euclidean topology, which does employ the metric topology, which is a special case, I mean, of the metric topology. And yeah, so that's all the examples I have for you before getting into quotient space or the quotient topology. So, where's my eraser? Okay, so you want to create a quotient out of this femboy space, huh? Let's do it. Okay. So, recall my discussion in the femboy expositions on math about quotient spaces. Not only quotient spaces, but quotient groups. So a set X can have on it an equivalence relation, which is this over here. And what this equivalence relation does is basically say points inside X or elements inside X are practically the same under some given condition. Like say Z, in Z mod 2, let's say, or prime number. I mean 2 is a prime number, of course. Let's say Z3. So 3 elements including the 1, 0, 1, 2, and then wraps back to 0. Then what we did here to construct this is to define an equivalence relation on the integers such that numbers beyond 3 are identified to be the same as, 3 and beyond, right, are identified to be the same as 0, 1, and 2 via some modular arithmetic, which means wrapping back around and stuff like that. And this is isomorphic to the cyclic group of order 3, but it's not the focus of today's lecture. What I want you guys to focus on is if this is a space, what exactly happens when we identify points on this space to be the same? I mean, if you think about it, like, think of a tortilla chip, alright? And I pick 2 points, and I say they're practically the same. It would make this big bulge, I would say. This is what it would look like. So what is our formalism for this idea over here, right? So this is a specific case of that, of course. And this is another way of constructing, of course. This is another construction. X identified on those parts. So we're going to focus first on one space, okay? Because a while ago we talked about 2 spaces and we talked about a subspace. Now we're only going to be talking about the space itself, okay? And of course, we're going to talk about a special subset of it, which is its boundary. Assuming it has a boundary, like closed disk. Okay, so I'm gonna have Q, or assume that Q has its own topology right now, tau sub Q. Of course, this is a subspace of F with its own topology. But that fact is not important. I'm just writing it out for you guys. Okay, so let this thing here that takes 2AB and then takes them to A identified with B be an equivalence relation on Q. So Q mod this thing, or Q quotient this, or what we call the quotient set, is the set of all equivalence classes under this here. So all A, such that A is inside Q. Alright. So this is the quotient set. So the equivalence class, of course, of A is every other element inside Q that is the same, quote unquote, to A. This is why it's the symbols like this. It's almost an equivalent. It's almost an equal sign, but it's not quite an equal sign, because we're saying that they are the same in a way, but not really. really the same. Okay, they're still distinct symbols. It's just that they're the same under this given condition, or they're just the same in this case. Okay. So I have a map. So I have a map Q that takes small q, that takes Q and maps it onto its quotient set. And that's characterized by, for any A, it is mapped onto its equivalence class under that equivalence relation, and this Q. This is called the canonical projection. Alright, so any femboy inside here, I project onto other femboys, or the set of every femboy that is similar to him under a given condition. Likewise here, any set, any femboy A inside Q. And what you may be thinking, what about another distinct femboy B inside Q? Well, it could just be A. It could even be inside the equivalence class of A, so we don't need to specify it. It could just be, say, any element in Q and then its equivalence class. And the equivalence class already absorbs other elements which we would think to be distinct in this set. Okay. Alright. So that's fun and all, but alright, let's formally do this. Let's formally construct its topology. And that begins with the basis. So for every subset or open set S inside Q mod its equivalence ratio, or the quotient set. Particularly S is inside Q and S is inside F, I think. Oh no, S, sorry, S is inside big S and S is inside Q. Okay. Okay, the following holds. So the reverse image, or the pre-image of this S is defined to be the union for all S inside big S of those images, and then small s. This is big S, by the way. And then that's equal to this over here, X, all X in Q, such that the equivalence class of X under the equivalence relation is inside S. Big S, by the way, not small s. So this here, or the family of all U such that this is true, right, is the basis of topology, of the quotient topology. So keep this property in mind. So take note of it, because I'm going to erase it. Alright. Let the family U inside basically Q mod the equivalence relation such that, the Q a while ago, Q to the minus 1 of big S is open inside the topology of Q. And be the topology. Or the basis of topology. Be the basis of the topology, called the quotient topology. So this U is an open set of femboys such that the canonical projection, or the reverse canonical projection of every S that's contained in this U is inside the topology of Q. Alright, so a lot of things have rhymed a lot in this lecture. So let me give it to you straight. So I have my original map that takes every single femboy and maps it onto the set. So it corresponds our given femboy with a set of all possible femboys that look like him or has the same attributes as him or is the same as him under our equivalence relation, of course. And then now, what I'm doing is just taking those or a collection of those, those group of femboys, not really group, but set of femboys or class of femboys, and they correspond it to a femboy, which is q to the minus 1. And if that q to the minus 1 is inside PQ, then this family of U is the basis for the topology called the quotient topology. And the full quotient topology is this over here. So the topology of Q mod the equivalence relation, which is that. So it's all these open sets U inside Q mod that equivalence relation, such that the canonical projection, or the pre-image of the canonical projection of S is inside the topology of Q. And that is the quotient topology. Now what we have to do is to complete the construction, is to say or to equip our Q, of course, mod the equivalence relation with this topology. And we're done. Or I think we need to do like that. We're done with our construction. Now, if we envision, of course, the certain subsets or these subsets U to be the boundary of Q, of course, then we can denote this space as simply Q identified with its boundary. So we can think of it as, a disk. I have a disk of femboys, and then I have its boundary. What I do is identify every single femboy along the boundary to be one singular femboy, and that essentially turns this into a sphere. So this thing mod its boundary gives something that is homeomorphic to the sphere. Or the femboy sphere at least. So that's one example of the quotient space. Another example, of course, that gives us practically the same result, but it doesn't, of course, imply a homeomorphism or direct homeomorphism. Actually, yeah, it does. It implies a homeomorphism. Is the unit square. So I have a unit square. Let's say all femboys that are bijective to the interval 0 to 1. Or all femboys that, of course, follow the structure. I just identify it via its boundary, which is just a regular square. And then it gives me something that is homeomorphic to this over here. And in fact, these two are homeomorphic. I can just bulge this out and get a disk. So this is where the geometric part comes in, of course. It's a good intuitional guide on the quotient space. So if I have an open shape, right? A shape that's two-dimensional, topological, gives a volume or one-dimensional volume element, topologically speaking, or it's two-dimensional, geometrically speaking. When I take its quotient space, it closes up the shape into a three-dimensional shape, geometrically speaking. And it turns it into a surface now. So it doesn't have volume anymore, it becomes the surface of that new surface. So that's something. Another example, of course, is the one we've done so many times already, which is the construction of FT2. One way of constructing FT2 is I take a unit square of femboys and then I identify them like this. First, identify these points via the quotient space. So we split the boundary. Or the quotient set of this into two quotient sets, and then create two topology or two quotient topologies for those, and then combine them together to get the actual topology of this shape. So I split the boundary into two subsets, which are these two, and then these two. And then I identify those boundaries separately. So first identify these two to get a cylinder. Oh, sorry. And then identify these two to get the actual final shape, which is the torus. So again, very important concept, because when we take away a subset, right, or we identify points, we're gonna need this thing. So, as I said, this is a very short lecture about the quotient topology. Very important concept. It will come up. So, this is a good place to stop.